Pluto made them come from the start. It was as if it was never really a segment of the nearby planet gathering's planetary moderate framework. Pluto's orbit crosses that of another planet, and that is no kind of lead for a planet. Pluto, the confounding, more modest individual planet at the edge of our planetary gathering, is causing a commotion in the cosmic neighborhood. Reports suggest a coming collision with Neptune, igniting concerns among scientists and space enthusiasts alike. Esteemed experts, including Neil deGrasse Tyson and Michio Kaku, have raised alarms about the potential consequences of the celestial clash. But how exactly did Pluto end up on a collision course with its distant neighbor? And how might this dramatic event affect our world on Earth? Join us as we dive into the surprising scenario unfolding between Pluto and Neptune. Pluto, once seen as a definite planet, was subsequently reclassified as a dwarf planet due to its unusual orbit. Nevertheless, this change hasn't stopped it from continuing to intrigue and captivate the astronomical community. Prominent figures, such as Neil deGrasse Tyson and Michio Kaku, have highlighted an unsettling proximity between Pluto's trajectory and that of Neptune. These experts are warning about a potential collision between the two planets, posing a significant risk to Earth. The peculiarity of Pluto's journey around the Sun lies in its unique characteristics within our local planetary system. Its orbit spans an impressive 248.8 years, and since its discovery in 1930, Pluto has not completed a full revolution. What adds to its intrigue is the highly elliptical nature of its orbit, a departure from the nearly circular orbits of the major planets. Moreover, Pluto's orbit is marked by a 17 degrees inclination to the ecliptic plane, making its path steeper compared to other planets. This combination of inclination and eccentricity introduces layers of complexity to Pluto's orbital pattern. A striking aspect of Pluto's orbit lies in its intersection with Neptune's path. For roughly 20 years in each cycle, Pluto ventures closer to the Sun than Neptune, challenging assumptions based on their respective positions in the solar system. This raises the question, why hasn't a collision between Pluto and Neptune occurred? The explanation lies in the gravitational influences exerted by other planets. The study of Pluto's orbit began shortly after its discovery, presenting astronomers with a remarkable course of study. Unlike most planets, whose orbits align relatively close to the ecliptic plane, Pluto's unique features include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit amidst these complexities serves as evidence of the intricacies inherent in celestial mechanics. The three-body problem in space mechanics involves understanding the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. It is akin to predicting their paths based on initial positions and mutual gravitational influences. In Pluto's case, this problem explains the intricate interplay between its orbit, Neptune's orbit, and the Sun's gravitational pull. Terms like apsidal libration, scope libration, and the VZK oscillation help unravel the celestial puzzle. Astrophysicists explain that apsidal libration, responsible for maintaining planets in their orbits, plays a crucial role in the case of Pluto and Neptune. This term signifies that when Pluto crosses Neptune's orbit, it is positioned roughly 90 degrees away from Neptune, critically preventing potential collisions. Scope libration, referring to the vertical movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it is positioned significantly above their orbital plane. This provides an added layer of protection against impacts. A key factor in understanding celestial motion is the VZK oscillation, named after three researchers, von Zeipel, Lilton, and Kozai, who studied the gravitational interactions among three space objects like Pluto, Neptune, and the Sun. The VZK oscillation explains why Pluto's orbit around the Sun appears erratic, yet remains stable over time. Despite the apparent chaos in space, underlying patterns and rules maintain order. These factors collectively stabilize Pluto's orbit, preventing collisions with Neptune or deviations from its path. The three-body problem helps us understand how the gravitational forces of these celestial objects influence their paths. Studying this enhances our knowledge of Pluto, the solar system, and distant celestial bodies. Numerical simulations in the late 1980s revealed that, despite its chaotic properties, Pluto's orbit is remarkably stable. Minor initial deviations may lead to significant differences over millions of years. Nevertheless, Pluto's unique orbit maintains stability over unimaginably long timescales, keeping chaos in check. Recent virtual simulations have improved our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun Neptune's orbital resonance, where it completes 3 orbits for every 2 of Pluto's, adds to stability. Jupiter's gravity also plays a significant role, while Saturn has a smaller impact. Together, these forces ensure Pluto's safe and stable movement through space for billions of years. These phenomena are crucial for maintaining order and consistency in the motions of objects in the universe. Without these elements, the solar system would be a place of greater chaos and unpredictability, potentially leading to collisions or ejections from stable orbits. Understanding Pluto's orbit is vital, particularly in discussions about a potential contact with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of our solar system. Pluto's case highlights the fact that seemingly unstable orbits can achieve harmony through the complex interplay of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are essential for gaining a better grasp of our place in the universe. Exploring the depths of space often reveals the eccentric nature of celestial bodies, and Pluto's orbit serves as a prime example of this unpredictability. The concept of orbital chaos, illustrating the delicate dependence of a celestial body's path on its initial conditions, is vividly demonstrated in Pluto's case. Even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Computational simulations have been instrumental in helping researchers understand how Pluto moves in space. These simulations utilize complex mathematical models to replicate the gravitational interactions among Pluto and other celestial bodies, such as Neptune. By making small adjustments in the simulations, space scientists can observe how minor changes can have a profound impact on Pluto's trajectory. In the late 1980s, these simulations uncovered a fascinating aspect of Pluto's orbit, despite factors like apsidal and scope libration contributing to its stability. Pluto's orbit can still exhibit unpredictability. Even a slight initial difference in Pluto's position or velocity can lead to substantial changes in its path over millennia. Despite this inherent chaos, Pluto's orbit remains stable over extraordinarily long periods, spanning billions of years. This suggests that, beneath its seemingly erratic appearance, Pluto's journey around the Sun follows an underlying order. Predicting the long-term behavior of celestial bodies, particularly those with irregular orbits like Pluto, is exceptionally challenging. The inherent unpredictability of these systems makes long-term forecasts uncertain. Mathematical simulations assist in understanding and anticipating the future paths of celestial bodies, but also reveal the limitations of our predictive capabilities. These models rely heavily on precise initial conditions and replicate complex interactions. Even a small error can lead to drastically different outcomes, making exact predictions difficult. The turbulent nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case underscores the limitations of our current knowledge. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how each planet's presence and position can influence the stability and trajectory of other celestial bodies within the system. Nevertheless, despite these intricate forces, prominent astrophysicists are now expressing concerns about a potential collision between Pluto and Neptune. This raises questions about why such a collision, which seems unlikely given the stabilizing factors, is now a topic of concern. Neil deGrasse Tyson, a a renowned astrophysicist known for popularizing astronomy, offers a unique perspective on the mysteries of our solar system, especially regarding Pluto, famous for advocating Pluto's reclassification as a dwarf planet rather than a true planet. Tyson provides insightful commentary on the evolving understanding of celestial mechanics. Tyson views Pluto's reclassification not as a demotion, but as a necessary adjustment to our growing comprehension of the diverse objects orbiting the Sun. His approach to celestial mechanics involves continuous learning and adaptation. He sees the complexity of orbits like Pluto's as a reminder of how much more there is to discover in space. Tyson believes the allure of these mysteries is what makes astronomy so fascinating. Moreover, he is aware of how space-related events and discoveries shape public interest in astronomy. Events like Pluto's reclassification and its peculiar orbit present opportunities to captivate the public's imagination and curiosity about the cosmos. By discussing the dynamic and sometimes chaotic aspects of space mechanics, Tyson opens a window for the public to engage with the intricate wonders of the universe. Similarly, Michio Kaku, another esteemed astrophysicist, has voiced concerns about the potential implications of a Pluto-Neptune collision. While the probability of such an event remains low due to the intricate interplay of gravitational forces, Kaku emphasizes the need for vigilance in monitoring these celestial bodies. The ongoing study of Pluto's orbit and its interactions with Neptune offers a valuable lens through which scientists can explore the delicate balance that governs the solar system. These investigations not only deepen our understanding of Pluto and its unique dynamics, but also provide critical insights into the mechanisms that ensure the stability of our cosmic neighborhood. In conclusion, Pluto's orbit, once viewed as chaotic and unpredictable, reveals a hidden order driven by the interplay of gravitational forces. The dwarf planet's peculiar path serves as a reminder of the complexity and beauty inherent in the universe. While concerns about potential collisions may persist, the study of these celestial phenomena continues to inspire awe and wonder, shedding light on the intricate workings of the cosmos.